So the next session is continuation of the previous sessions, and we'll talk a bit about distortion and the effect on the analysis, and we'll have an introduction to some meshing strategies that take into consideration the effects of distortion. Okay, so if we go back to what we've covered in previous sessions, we talked about what we need for accurate analysis results, different meshing types, element types, the order of elements, the effect of the relationship between the accuracy and the computational cost of different element types. In this session, we'll talk a bit more about distortion. In the previous session, we started with that. And the bit in yellow is we'll start talking about meshing strategies for some shell and solid models. In the sessions that's coming, we'll spend a bit more time on different meshing strategies for specific, more interesting geometry types and complicated structures to mesh. And then in later sessions, the last bit is what will then what's still coming. So talking about beam modeling and how to mix beam and shell and solid models together. Okay, so previously we already discussed what the best possible accuracy is for different element types. Where that comes from is the number of degrees of freedom. We need those to be able to move the element without generating a stress, but we also have only so many variables to calculate certain results with. So as an example, if I look at the first order tetrahedron element, tet element for short, it can only represent the constant stress in the x, the y, and the z direction, the constant shear in each of the three directions as well. The element cannot model any stress gradients. Okay, if I look at the first order hexahedron element on the other hand, we've also got all of the constant stress components. But in addition to that, we have linear variations in some of the components, like the stress in the x direction can vary in the y and the z direction, the stress in the y can vary in x and z, and so on. So for less degrees of freedom, I can have a significantly more accurate results using hexahedron elements than tetrahedron elements, simply based on this. Okay. One problem that we have is that was the perfect element, which doesn't quite exist. There's quite a few formulations and some of them come close, some not that close. But any type of distortion from the perfect shape degrades its accuracy. If I look at, for example, a first order quad element, so there's some images. So the one on the left, this is the perfect element. Quad element wants to be perfectly square. The second option is the aspect ratio, so we make it longer in one direction, shorter in another. In other words, it's a rectangle shape, a parallelogram, and a taper where it's longer on one side and shorter on the other side. These are some of the most common distortion types. There is another one that I'll get to in a moment. So any distortion is actually a combination of a series of these, because it's very seldom that I only have this or only this. There'll be some of a couple of these. The last one is a warped element. So that is where it's bent out of plane. So in other words, I take those two corner nodes and I lock them into place there and I move the other two up. The problem is, this actually shows you nicely why this is a problem. On the left-hand side, there is a valid solution for that shape, and on the right-hand side, the exact same node locations, but it's a totally different shape. To prove that, I just drawn them both, and these lines in kind of brown is the bottom one's edges, and you can see it comes to exactly the same corners. So in other words, exactly the same node movement gets me two different possible shapes. In reality, what the finite element method will do is it'll actually combine these two shapes. Now, to see why this is an issue, if I look at this one, for example, it's very stiff if I try to bend it about that axis, but it's really easy to bend about an axis that's parallel to that length direction for this circular shape. While this one is very easy to bend about that axis, but on this angle, again, it's very stiff. Now, if you combine the two, so there is kind of halfway, we get some really weirdly distorted shape. And from that, it then ends up being stiff in two directions, which is not quite representative of reality. Okay, so what does distortion cause in terms of elements and accuracy? So the first is the higher order stress and strain terms are reducing in terms of its accuracy. In other words, if I have something like the X element that I spoke about earlier, which can have constant stresses in addition to gradients in the X and the Y and the Z, these gradient terms becomes less and less accurate to the point where if it's really distorted, it becomes similar to a constant stress element. So in other words, a really badly distorted X element will behave as badly as a first order TET element. As part of that also, we start to overestimate the stiffness of the element. So this previous example of that warped element was a nice example that'll change its bending stiffness. But all of the other effects, trapezium shapes, parallelograms, aspect ratio, all of those will also change and overestimate usually the stiffness of the element. So if the stiffness of the element is overpredicted, the stiffness of the complete structure can also be overpredicted, and then with that, it can also degrade the stresses even further. Okay, now, once we get to really, really extremely distorted elements, we start getting what software often calls an inside-out element. It may tell you that the Jacobians are negative. It's simply the same thing. What it says is some of the integration points lies outside of the element, which kind of doesn't make sense. So these elements are not just inaccurate, they're utterly invalid. It's not possible to solve those, or if you mathematically try to solve them, they're kind of unstable as well. So it's a really bad idea to try and do something like that. So here's an example for a first order element. So the red bits are the corner nodes. And if I take that and I move that node in this direction, I end up with something looking like this. And this is a quad element, but it looks like a kind of a weirdly stretched and collapsed star element almost. At this point, some of these integration points is actually moved slightly to the outside of that, and this element will be singular. It won't be possible to solve. If I get to second order elements, they tend to be less sensitive to certain types of distortion, but they're very sensitive to mid-node distortion. So if I take this shape and I start moving that node a bit down, I get a parabolic shape for that one, and the same parabolic there. And this is what you see on this example. If I move it a lot further, I start getting this kind of extreme case where these edges is actually crossing over each other. Where they cross over each other, we end up with a part that's well outside of the element while trying to be inside of the element as well. So again, this element, long before we get to this level of distortion, is actually an invalid element already. Now this is something we get a lot when we try and project mid-nodes onto sharp radii and stuff. So it's entirely possible, even before something like this happens, if I bring these nodes closer together, I can get this edge to start overlapping with that one or this one as well. So again, the same kind of a problem. Okay, so why is distortion important? Because the mesh accuracy is determined by the element type, whether we're looking at, for example, tri-quad elements or TET or X elements, whether the element is first or second order, possibly even higher order, but also the mesh density for the given element type. So that said, if I pick a tri-mesh, I have to mesh a lot finer for the same accuracy than the quad mesh. And this means that effectively the mesh density for the tri-mesh, even if it's a lot finer for the same accuracy, it's there's a certain level of accuracy related to this. Okay, so the last one is the degradation of the element accuracy due to distortion. So if I have a nice element, really good mesh density, but I've got distorted elements, you start getting the effect as if it was a significantly worse mesh that you had. Okay, so in the next couple of slides, I'll start talking a bit about meshing strategies and say some interesting effects and so on. So what we're trying to do with a mesh is we're trying to balance accuracy, how long it takes to mesh and how long it takes to run. Obviously, to get more accurate answers, I can mesh a lot finer. The mesh time is heavily influenced by the kind of elements I use. For example, X elements are significantly more painful to mesh with than TET elements, for example, but they make up for it in terms of runtime. Okay, so all of these can have a significant impact on the runtime. So that element choice, for example, if I look at meshing a TET element, it's really, really easy to mesh. It's really fast to mesh. Typically, any complex shape, you select it, you specify an element size, and you click the mesh button, and it goes. Runtime is usually slow. So I'll get back to this usually because there are actually cases when it's better than AX mesh in runtime. If I look at the hexahedron element, unless it's a very simple shape, it is more effort, and in some cases a lot more effort to mesh than a tetrahedron element. And in some extreme cases, you get certain shapes where it's impossible to get decent quality X elements. So that may again make it worthwhile to consider at least 8 elements. The upside of the hexahedron element is the runtime is usually pretty decent. Some cases 10 times faster than a tetrahedron element will be for the same accuracy. And that assumes this is a second order tet. First order tets can't even compete for most kinds of model. There are a couple that actually is useful. Okay. So if I've got an analysis and I've already picked my element type and whatever, I'm happy, but now I want to improve my accuracy. The only thing I can then do if I want to keep that same element is I need to mesh finer. So if I halve the mesh size for, let's say, a quad mesh, I end up with 4 times as many elements, meaning it will run at least 4 times, probably 6 or 7 times longer. If I look at solid elements, that'll be third order. So half the element size will mean 8 times as many elements, meaning significantly more than 8 times longer runtime. So that's one way to do it. By simply meshing finer, we'll usually end up with significantly longer runtime. An alternative is to mesh efficiently. By that I mean if you know or have an idea where we expect stress concentrations, in other words, high stress gradients, we need a finer mesh in these areas. In areas where there's either no or very little stress gradients, we can mesh coarser. So you spend a bit of more effort in terms of meshing, but you can get significant speed-ups in accuracy, significant speed-ups while still getting a better accuracy. So here's a nice example. If I look at the bottom left, this is, let's say, relatively speaking, this is 2 millimeter elements, and I see a maximum stress of 376. Now this is, if I combine all of these, I've got a load pointing to the left and the right, an edge load applied, but I've just split it so that I can look at different measures for exactly the same state. So these are symmetry models, but you could just as well have run a full model. It'll just be a lot more expensive. So in this case, 170 elements, and the maximum stress is kind of as expected at the thinnest section, 376. The one on the right had almost the same number of elements, but we tried to simply specify more elements there, but kept the 2 millimeter elements. What's interesting is the stress actually came down a bit. And what causes it is there where we've got the highest gradient is also, that element is more distorted than this one. So it shows you again that distortion is significantly important. Now there's another interesting one there as well that you can see on both of these. That last element has got more than half of the stress contours just in that one. So it's got an extreme stress gradient compared to pretty much anything next to it. So if we can reduce the element size there, both in this direction and in this direction, but especially that direction, we expect to see a significantly better answer. Okay, so if we go simply refine the whole mesh, so I specify 1 millimeter instead of 2 millimeter elements, stress goes from 376 predicted to 394 predicted. You can also see the stress patterns are a lot smoother, especially in this area, so I expect this is significantly more accurate than this simply based on how kind of jagged these values are. On the right-hand side, I split out a small section so that I can get the really good quality elements there. And you'll notice that there is a bit of aspect ratio distortion, but no others. In this case, that size is 1 millimeter, similar to this, but it went down to 0.4 millimeters on this edge. And then radially also, I expanded the element size from small to large. So we've got a smaller element in that region. And then the rest I mesh with 3 millimeter elements. So it's significantly larger even over there than it is in this model. If I compare these two, it's only slightly more elements and it's significantly less than this one, but the stress predicted is even closer to what the reality should be. So we can still zoom in and zoom in there to see what the actual stress state at that location is. So this is one of the things you may have to do in a model, and in a lot of cases we try to do is to try and improve the mesh density in areas where we expect high stress gradients. In other words, where the bad stuff happens also in models. Okay, then we'll look at a couple of cases of some, well, kind of, not so terribly difficult, but some difficult geometry that causes issues. This is an example of a region where if you mesh finer, your mesh gets worse. In most cases, the refining improves the mesh, but this is one of the cases where it's exact opposite. So I'll start with a fine mesh. And in that region, I've just zoomed in a little bit there, and I'll zoom in a bit more. So if you look at this, see there's two badly squashed tri-elements there, and on the other side as well, and there's a really badly quadrant. The same goes for the other side. If I mesh coarser, this is actually zoomed out, so this element is a lot larger, but you can see now, yes, there's tri-elements, but even the tri-elements is less distorted, and the quad elements next to it is actually pretty decent shape. The reason for this is as we try and mesh finer and finer, we're getting into closer and closer to a totally squashed element, totally collapsed element. In other words, the internal angle is close to zero. Okay, now in this case, both of these are actually surprisingly okay, even that bad element there, simply because I allowed tri-elements in this model. If I force it to only use quads, there'll be a really horrible element in that location. There's no way that something like this can work. Good. So one of the possible fixes in something like this, now this I've suppressed that whole edge, but usually you only need to suppress a small region surrounding that. So the reason this problem occurred was because that edge and this edge comes together at a 0 degree angle. So by suppressing that, it can now mesh elements and it doesn't need to attach to that edge at that location. So this is a significantly finer mesh than the previous one, and as you can see, there's no issues with bad elements in this location. Actually, the mesh in general looks a lot better, except we unfortunately now end up with the warped kind of elements in this region. Anyway, mesh coarser, even with the coarser mesh, you see the warping a bit more, but still this allows, whether it's fine or coarse, to have better elements in this region at least. I don't have those collapsed elements. So, yes, I know it's still not a perfect solution. The best solution in theory would have been if it was possible to move this hole either slightly into that or slightly out of this. In that case, it's not that infinitely sharp corner that we end up with, which means as we mesh finer, the mesh will at some point stabilize and start giving reasonable meshes. Okay, another difficult kind of geometry, it's actually not that hard, but it's easy to do it really, really badly, is if I look at shafts. A typical shaft like this, I want to mold this with solids, I want to keep the radii and stuff. If we try and let's say split it into a section, mesh the one face and then revolve it, we end up with really bad elements in this region. So what's already obvious there is that element outside may be close to perfect aspect ratio, but as you move in the other two directions, it's about the same size, but in that direction, the theta direction, in other words, the circumferential direction, the element starts getting smaller and smaller until, if I zoom in there, these elements are really, really horrible. So it's large in this direction and a fraction of a millimeter size in that direction. Okay, so this is a bad way to model things. The alternative is, if I split this, again, previously I would have meshed this whole section and revolved. Now I start looking at the concept of meshing different parts of it in different directions. So the reason I want to do that is if I mesh this and I revolve, there's no matter at what radius, there's the same number of elements in the circumferential direction. Okay, so if I mesh the green sections and I extrude them actually, in other words, I mesh this face and extrude it in that direction, and I'm talking as if I'm doing it manually, but it's just explaining how it happens in the background. So your measure can do it on its own for all that I care. Okay, so in that case, it allows me to have different elements on that inner edge as the outer one, the same different number there and there. And this, I can have any kind of a mesh on that front face. On these though, it's not possible to mesh this and extrude in that direction. There are a couple of methods that will allow something like that. So if this was a straight section, I could in theory have had an element at an angle like that. You usually get pretty bad meshes if you try and force something like this, but it is possible to do that. Okay, so instead, if I mesh these blue faces on this face and extrude it in the radial, or sorry, in the theta direction, the circumferential direction, I end up with a mesh looking something like this. I'm just looking at it from that side now, and there you can see it's quad elements all the way. There may be one or two tries, but they'll be almost non-existent. We've got nearly perfect elements on the inside. We've got really good elements there. All of these regions on this side is not necessarily perfect. I could have improved the mesh there, I agree, but it's still pretty decent. And now I'm extruding it in the theta direction. This section again, I'm extruding in this direction because I want less elements there than there, so that the element size in that direction stays more or less constant. And I do the same for the last one as well. Okay, so this will result in both a significantly reduced number of elements and a significantly improved accuracy of the model, because the distortion level of the elements and the number of distorted elements are actually significantly less. So, yeah, this was a pretty short section. We just started talking about the meshing strategies. There's just two simple examples. In a future session, we'll spend time purely on just different meshing strategies for specifically shells and solids. And then later on, as I say, we look at beams, shells, solids, and so on methods as well. Okay, thank you for your time.